Welcome to the new project. Imagine playing rock, paper, scissors where your mouse and keyboard don't matter at all, your hand does. Instead of clicking buttons, you hold up a real hand sign in front of the camera, and the game decides your move by watching you in real time. In this project, we're building Rock, Paper, Scissors game, a computer vision-powered game that combines a live webcam, a trained YOLO model, and a Flask web app. The twist is that you're not just trying to win randomly. Each round gives you a clear mission, win, lose, or draw, and your challenge is to control your hand gesture precisely at the right moment to satisfy that mission. By the end of this project, you'll see how Python handles the heavy lifting, camera input, model inference, and game logic, while the browser turns those results into a smooth game-like experience. You're not just learning how to detect rock, paper, or scissors. You're learning how to connect AI to an actual product people can play with. Okay, let's get started. Now let's zoom in on what we're actually going to build. In this project, we're creating Rock, Paper, Scissors Mission Game, a camera-based game where your real hand gestures become the controller, and an AI model decides what move you played. The goal of this app is simple and exciting. It uses a live camera and a trained AI model to recognize your hand gesture as rock, paper, or scissors. Instead of just playing normally, each round gives you a mission such as win, lose, or draw. Your task is to show the correct hand sign at the right moment to clear that mission and earn points. When the program runs, you'll see a live camera view on the screen with detection boxes showing what the AI sees. The computer chooses its hand in advance and displays it on the screen. You'll also see a mission like please make it a draw. A countdown starts, and when it reaches go, you hold your hand steady. For example, in round 1, the mission is draw, you show paper, the computer shows paper, and the result is a draw. In another round, the mission is win, you show rock, the computer shows scissors, and you successfully clear the mission. The score updates after each round, and the game continues for 5 rounds in total. Behind the scenes, this project covers several important Python concepts. You'll see how variables are used to store the current round, score, and detected actions. Conditional logic is used to decide win, lose, or draw. Loops control the flow of multiple rounds. You'll also learn how Python works with a web framework to handle requests, manage real-time state, and connect AI predictions to game logic. This project is a great example of how Python can go beyond simple scripts and become part of an interactive application that feels like a real product. In the next step, we'll walk through the project structure and start breaking down how each part works, one piece at a time. Now let's take a look at how this project is organized by walking through the file structure. At the top level, this project is built like a typical Python web application. The main entry point is app.py, which controls the entire application. This file starts the web server, loads the AI model, connects the camera, and defines the routes that the browser talks to during the game. The static folder is used for files that the browser needs directly. Inside it, the JS folder contains game.js, which handles the game flow on the screen, such as starting rounds, running the countdown, and updating the score. Still inside static, the RPS folder holds the image files for rock, paper, and scissors. These images are shown when the computer reveals its move. The templates folder contains index.html. This file defines the layout of the web page you see in the browser, including the camera view, the mission text, the countdown, and the result panels. Flask connects this HTML file to Python so the page can display live data. There is also a weights folder which contains the trained AI model file called bestpt. This file comes from a previous project where the model was trained to recognize hand gestures. In this project, we are reusing that trained model instead of training a new one from scratch. Overall, this structure separates responsibilities clearly. Python code lives in app.py. Visual layout lives in index.html, browser logic lives in the JavaScript file, and AI data lives in the weights folder. This separation helps keep the project clean and easier to understand. In the next step, we'll zoom in on app.py and start exploring how the main application logic works in detail. Now let's focus on the structure of app.python file, which is the core of this entire project. This single file is responsible for connecting the camera, running the AI model, handling the game logic, and communicating with the web page. At the top of the file, we start by importing the libraries we need. These include standard Python modules for time control, randomness, threading, and unique IDs, along with external libraries like OpenCV for camera access, Flask for the web application, and YOLO for AI inference. This setup tells us right away that this file handles both web logic and real-time computer vision. Next, the Flask app is created. This is what allows Python to act as a web server. After that, you'll see a configuration section where things like the model path, camera settings, and valid game actions are defined. Keeping these values in one place makes the app easier to adjust and understand. Then comes the shared state section. This part is very important because the camera runs continuously in the background. Variables here store the latest detected hand action, its confidence level, and the most recent camera frame. After that, we move into the game logic. This is where Python decides whether the result of a round is a win, lose, or draw based on the user hand and the computer hand. This logic is simple, readable, and easy to test, which is ideal for beginners. One of the most interesting parts is the camera loop. This function runs in a separate thread and never stops while the app is running. It reads frames from the camera, sends them to the AI model, extracts the best prediction, and stores the result in shared variables. At the same time, it prepares annotated frames so the browser can display live detection results. Below that, you'll see the route definitions. These routes are how the browser talks to Python. One route renders the main page, another streams live camera images, another starts a new round by generating a mission and computer choice, and another judges the results using the latest AI prediction. Each route has a clear responsibility, which helps keep the code organized. Finally, at the bottom of the file, the app is started. This tells Python to run the server so the game can be accessed through the browser. Overall, app.py acts as the brain of the project. It connects AI, game rules, and web communication in one place, making everything work together smoothly. In the next step, we'll move on to index.html and look at how the user interface is built and how it connects visually to this Python logic. Now let's take a closer look at the structure of index.html, which defines everything you see in the browser. This file is responsible for the layout, the visual sections, and how the user interacts with the game on screen. At the top of the file, the document starts with the standard HTML setup. The head section includes basic metadata, the page title, and a link to Bootstrap. Bootstrap handles the styling and layout, so we can build a clean interface without writing a lot of custom CSS. Inside the body, the entire page is wrapped in a container. This keeps the content centered and gives the page consistent spacing. Near the top, there is a title area that shows the game name and the start button. This is the main entry point for the user to begin the game. Below that, the page is divided into two main columns using the Bootstrap grid system. The left side is dedicated to the live camera, and the right side is used for the game panel, which includes the mission, score, countdown, and results. At the bottom of the file, the required JavaScript files are loaded. First, the Bootstrap script is included to support interactive components. Then the game logic script is loaded. This script connects the user actions on the page to the back-end routes and controls how the game progresses. Overall, index.html acts as the visual layer of the project. It does not contain any AI or game logic itself. Instead, it focuses on structure and presentation, while Python and JavaScript handle the behavior. In the next step, we'll zoom in on the left camera section and look at how the live video stream is embedded and displayed on the page. Now let's zoom in on the left camera section, which is where the AI and the user actually meet. This part of the page is built as a Bootstrap card, clearly separated from the rest of the interface. At the top of the card, there is a simple header that labels the area as Live Camera. along with a small badge indicating that YOLO detection is running. This immediately tells the user that what they are seeing is not just a normal video feed, but an AI-powered one. Inside the card body, the most important element is the image tag. Instead of showing a static image or a video file, this image points to the video feed route from the Python backend. Because of this, the browser keeps receiving updated frames, which creates the effect of a live video stream. This is how the camera view and the AI detection boxes appear in real time on the screen. The camera area is wrapped in a responsive container with a 16:9 ratio. Below the camera view, there is a small tip section. This is a simple but important user experience detail. It reminds the player to keep their hands steady until go appears in the countdown. Since the AI reads the most recent frame at the judging moment, this guidance helps the player get more accurate results. Overall, the left camera section acts as the input side of the game. It captures real-world movement, shows what the AI sees, and prepares the data that will later be judged by the game logic. In the next step, we'll move to the right game panel and break down how missions, countdowns, results, and scoring are structured on the screen. Now let's break down the right game panel, which is where the game logic becomes visible to the player and where most of the interaction happens. At the top of this panel, there is a header section that shows the mission, the current round number, and the score. The mission text is placed front and center so the player always knows what they are trying to achieve. On the opposite side, the score display shows how many missions have been cleared out of the total number of rounds. Just below that, you can see the round indicator and a small status badge that changes as the game progresses. Below the header, the next section is the computer hand display. This area shows the computer's chosen hand using both an image and text. A key detail here is that the computer hand is revealed before the countdown starts. This gives the player time to think and choose the correct hand sign to satisfy the mission, rather than reacting blindly. Under the computer hand, there is a countdown section. This is a large, clearly visible number that changes from 3 to 2 to 1 and then go. The countdown creates tension, and also defines the exact moment when the player's hand gesture will be judged by the system. The bottom part of the game panel is split into two columns. On the left, the player's detected action is shown along with the confidence score from the AI model. This helps the player understand what the AI recognized and how confident it was. On the right, the round result is displayed, showing whether the outcome was a win, lose, or draw. A badge next to it visually reinforces the result. At the very bottom, there is a short explanation of the scoring rule, reminding the player that 1 point is awarded when the mission is cleared. This keeps the rules simple and easy to remember. Overall, the right game panel acts as the feedback and control center of the game. It guides the player through each round, clearly shows what is happening, and makes the results easy to understand. In the next step, we'll move on to Game.js and see how all of these elements are updated dynamically during gameplay. Now let's look at the structure of Game.js, which acts as the controller for everything that happens on the screen during the game. At the very top of this file, the code starts by getting elements from the HTML page. Each line connects a JavaScript variable to a specific element in index.html using its ID. For example, the start button in the HTML is linked to the start button variable here. This connection allows JavaScript to update text, images, badges, and counters dynamically while the game is running. Next, you'll see a section where basic game settings are defined. This includes the total number of rounds. By keeping this value in one place, the game length can be changed easily without touching the rest of the logic. After that, several helper functions are defined. These functions are responsible for small but important tasks, such as updating the computer hand image, changing result badges, showing the mission text, and resetting the user interface between rounds. Splitting these actions into functions keeps the code readable and avoids repetition. Then we move into the timing logic. There is a small sleep utility that pauses execution for a short time, and a countdown function that updates the countdown text from 3 to 2 to 1 and then go. This is what creates the game-like rhythm instead of everything happening instantly. The core of the file is the round logic. One function handles a single round from start to finish. It asks the backend to start a new round, displays the mission and computer hand, runs the countdown, sends a request to judge the result, and then updates the screen with the detected action, confidence, and score. Also, there is a session-level function that runs multiple rounds in sequence. This function disables the start button while the game is running, loops through each round, and then re-enables the button when the session is finished. Finally, at the bottom of the file, an event listener is added to the start button. This tells the browser to begin the game when the user clicks Start. The file also sets an initial state so the screen looks clean before the first game begins. Overall, Game.js is the bridge between the user interface and the Python backend. It does not perform AI detection or game rule decisions itself. Instead, it coordinates user actions, timing, and screen updates based on data returned from the server. Now that we understand how all the files are structured, we're ready to start updating the code. In the next step, we'll begin by modifying app.py and work through each part step by step.